Beer's law is this. It just says that the absorbance is equal to some constant times the concentration, C. In other words, it just says that there's a linear relationship between the absorbance, Y, the constant would be M, C would be X, and B, the intercept, is 0. That is, if we had 0 concentration, we should have 0 absorbance, the peak. If we, let's say, if we double the concentration, the absorbance should do what? Double. And so if I doubled this concentration, the absorbance should, the peak should double in height. If I cut the concentration in half, the peak should decrease by half. And so this peak grows or shrinks depending on the concentration, because the absorbance is going to grow or shrink. And what Beer's law does is it plots the relationship between absorbance and concentration. And so if we plot absorbance on the y-axis and then concentration on the x-axis, then a Beer's law plot would look something like this. If I have 0 concentration, I'll have 0 absorbance. As I increase the concentration, the absorbance increases. So if I double the concentration, the absorbance doubles. If I triple the concentration, the absorbance triples, and so on. But does this relationship hold over a wide range? No. It turns out you'll reach a point where it no longer does that. You'll reach a point where we might double or we might triple the concentration, but the absorbance barely climbs. And so what we have 2 regions of plot here. We have this first region at dilute concentrations. And then we have the second region at high concentrations here. At high concentrations, Beer's law fails. And so here, this would be high concentrations. Beer's law fails. We don't get this nice linear relationship. Well, what is high concentration and what is low concentration? Well, high concentration and low concentration aren't a fixed number. They aren't a fixed number because of this. When we look at Beer's law proper, what this constant consists of is something called epsilon and L. Epsilon is the molar absorptivity, or the extinction coefficient. L is the path length of the cuvette. Our cuvettes are 1 centimeter. And so L for us is just 1. What is high concentration and what is low concentration depends on the molar absorptivity. The molar absorptivity tells us how well or how poorly this species absorbs photons, those particular photons. And so high concentration, well, that depends on what we're talking about. And so rather than that, using absorbance is much easier. It turns out that high concentrations would correspond to an absorbance greater than 1. And so once we get to absorbances higher than 1, it starts to go nonlinear, and it's outside the Beer's law region. But absorbances between 0 and 1 should be linear, and these are relatively low concentrations, and therefore we get a nice Beer's law relationship here. And so just eyeball your absorbance there. Actually, you don't have to eyeball. There are 2 ways to get your absorbance. One, just hit the stop, the little stop on the bottom left. Hit the stop, If it's asking you to overwrite it, go ahead and discard. We don't need to save the data for this. When you hit stop, you get a little line on the spectrum with two arrows. Do you see it? And in the upper right, you see the absorbance reading. On the lower right, you see the wavelength. What is the absorbance reading? The peak. 1.833. Mine is 1.993. 1.955. Is that inside the Beer's Law region or outside the Beer's Law region? That's outside. And so we're in this nonlinear region. If we were in the Beer's Law region, we could do a 1 to 2 dilution, and the absorbance should be cut in half. But since we're outside the Beer's Law region, what we want to do is we want to bring the absorbance down to about 1. And so what we're going to do is we're going to just do some crude solution dilutions. And so what I'm going to do is I'm going to take this and dump out, let's dump out 2/3 of this. And so I'll just get a waste speaker here, or actually down the sink is probably okay with this stuff. If you accidentally pour more, then fill it up to about 1/3. I poured out too much. So I'm going to do a 1 to 3 dilution. A 1 to 3 dilution is 1 part crystal violet, 3 parts total, so 2 parts water. 1 part crystal violet, 2 parts water gives me a 1 to 3 dilution. So 1 to 3 dilution, if we were in the Beer's Law region, a 1 to 3 dilution would mean we would be at about 0.3. No, I mean 1/3 of whatever you're starting. So 1/3 of 2 would be about 0.7. All right. Once you do your 1 to 3 dilution, let's put the sample back in and see what the absorbance comes out to. So put the sample back in, hit play. We don't have to recalibrate this. I'm going to discard the previous. We don't have to save those either. We're just playing around. Let it take a few scans. When it looks like the peak is pretty stable, hit the stop. And then tell me what your absorbance is now. It's less. Is it 1/3 less? Because we just did a 1/3 dilution. So according to Beer's Law, it should be 1/3 less. So if you started at 2, you would be at 2/3, 0.7. Are you about 0.7? You are? Oh, all right. That's pretty good then. Mine is not. Mine went from 2 to 1.4. Uh-huh.
It stayed the same.
Impossible. You're good? Okay. What are you guys at as far as absorbance readings go? You're at 2? Did you do a 1 to 3 dilution? You did a 1 to 3 dilution and you're still at absorbance of about 2?
Yeah.
This is a bit high. What did you guys get?
0.988.
0.988? Okay, that sounds about right. So we're in the ballpark. And so, this is it. There is some trial and error. Because if this is too concentrated, which it is, we're outside the Beer's Law region. And we are going to have this nonlinear relationship. And so what we have to do is we have to make sure we dilute it down to the Beer's Law region. And that requires some trial and error. So I need to dilute it more because I'm at a 1.4. Just where we want to be is we want to start slightly above 1. That would be the best. And so, but this was a very crude solution dilution. The reason we want to start our experiment around this concentration and then watch as the crystal violet concentration goes down. And so let's do this. Let's dump out half of this and let's do a 1-to-2 dilution. And so if I dump out half and then top it off with water, so it's 1 part crystal violet, 1 part water, that's a 1-to-2 dilution.
Wait, can you put a new batch of violet, or is it the same?
I'm sorry?
Is it the one that was previously diluted?
Yeah. Yeah. So take your current cuvette and dump out half of it. Now we're getting closer to the Beer's Law region, right? And so if we dump out half and do a 1-to-2 dilution, what should the absorbance be? The absorbance should be 1/2 of what you just had. And so let's check it. But before you, actually, let's discard that. Okay, what did you guys get? Did you guys get about half the absorbance? Yeah? Oh, that's good. That's what we expect. So if we start off here and we cut the concentration in half, then we should have half the absorbance. But does that occur in the entire spectrum? No. That only occurs at one place in the spectrum. And that one place we give a special name to. The one place in the spectrum that occurs is called lambda max. Lambda for wavelength, max for what? Lambda stands for wavelength, max stands for lambda max. Have you heard of lambda max before? When you do Beer's Law is always this, absorbance at lambda max. Even though sometimes people don't write it, it's always absorbance at lambda max. Because did the whole spectrum, did the entire full spectrum just decrease in half? It turns out no, only lambda max did. Now what does max stand for? Lambda's wavelength, max stands for? Yeah, right. Max stands for maximum absorbance, so it's a wavelength at maximum absorbance. Let's find out what our lambda max is in this spectrum. And so on the bottom right, it'll tell you this is going to pick the highest point on the peak, and then it'll tell you what wavelength that occurred at. And so record your absorbance and then take a look. What's the wavelength? On the bottom right? All right, I have 591.1. So there's some variation, but that's okay.
So there was like slight variation from when we first started with the pure sample.
Yeah.
It kind of goes back and forth. What's that supposed to be?
Well, because that peak is too big. You know, when you have a big noise spike in an audio system, it'll flatten out, plateau. That's what you're seeing there. It's too high, the absorbance reading is.
For trial 1?
For trial 1,
Okay,
right.
so then for trial 2, the wavelength or the lambda max was slightly to the right.
Slightly to the right, okay.
And now it's slightly to the left.
Slightly to the left. Okay, let's do it again and see where it comes out. So now we're going to let's do another 1-to-2 dilution. Oh. And so dump out half of this, roughly. Doesn't have to be perfect because this is just eyeball. Diluted. And then let's remeasure it. So this run should be 1/2 the previous run, or 1/4 the run before that. All right, did you guys get this one? First, the absorbance. Is the absorbance about 1/2 the previous one and about 1/4 the one before that? Okay, that's good. That means we're in the Beer's Law region. It's working pretty good. The next thing is lambda max. Where's lambda max? So it's slightly different, right? It's always going to be slightly different because of the way this thing picks the peak. The way this thing picks the peak is it picks it based on the data point. It doesn't pick it based on what we call a curve fit. And so it's not supposed to be moving like that. It's just because, how many data points make this line? When you see this line, it looks like a smooth, continuous one, but there's gaps, right? And those gaps are at 1/10 of a nanometer. And so we have these gaps. So what it does is it just picks, and the way it draws the line is it tries to go through every single point. Normally, with these gaps, we try to smooth out. And so what we do is we use mathematical functions to figure out what's between the gaps and how the curve rises. And so sometimes you'll see something like this, You'll see two data points that are right next to each other like this. And if you zoom in, what you're going to see is you're going to see a flat plateau. Maybe this side's a little bit higher because of the way it fits this. But in reality, we have a gap here, and in reality, that gap is missing the peak. If we took one more data point, or a few more data points in between these, we'd see the peak rises up like this. And so because of this plateau, one side might be higher than the other side, which means it moves around, right? But that's the problem with this LabQuest system. If you use some really sophisticated graphing, what that does is it fits it to a mathematical function so we can figure out what the curve would have looked like had we taken data in between the data points. We don't have high resolution with this because this is only a $200 spectrometer. Higher resolution spectrometers are like $5,000, $6,000. And so we're going to have gaps there, and that means we're going to have some more susceptibility to error. Okay? But you have to blow it up, to a high magnification level to see the gaps, which we will in the Excel lab. We'll see these things when we do some other labs. All right, so we're in the Beer's Law region. It's working good. So what you want to do is you want to record your lambda max. What should you use for your lambda max? You could just average those or just pick one. Even if you pick one, we're still going to be close enough that we should get a nice Beer's Law. I mean, a 0.5 nanometer difference is not going to cause you too much trouble compared to the precision of this instrument anyway. I mean, if we were using a $5,000 spectrometer, it would be a different story. We'd want to be a little more precise. All right, now did the wavelength, if we do you see there's scroll buttons here? So we can move the little scroll bar to the right or to the left. And so let's move the scroll bar out to 760 and then see what it is. If we move it out to 760, do you see the absorbance? What's happening with the absorbance?
Going up and down.
Yeah, it's gone. And then by the time we get to 760, or actually we don't even have to get to 760. Let's go to 670. By the time we get to 670, it's flat lined. It's down to about 0. Does everybody see that? And when you're at 670, does the absorbance change much? No, it's just going to change because of random noise fluctuations that we're going to have. So it's going to just hover around 0. You know, sometimes it'll be less than 0, sometimes it'll be above 0. But if we did measurements on the shoulder there, we're just going to get things that fluctuate around 0. And so we really have to be at lambda max for this to work at the top of the peak. Okay, any questions on this? In Chem 1A, what you would have done is you would have, rather than eyeballing our solution dilutions, you would have used pipettes in volumetric glasswares to make certain dilutions, like a 1 in 10 dilution, 1 in 3 dilution, 1 in whatever dilution. And then we would have measured the absorbance, and then we would have come up with a Beer's law plot like this. From the Beer's law plot, we get the slope. From the slope, we get the constant. From the constant, we know what L is. We can solve for epsilon. And so a Beer's law plot like that, we're primarily interested in getting the slope. Well, for us, we're going to skip the Beer's law plot. We're going to use epsilon out of the scientific literature. And so I'm going to give you the value of epsilon so we don't have to do this calibration here. So what we're going to do is this. We're going to monitor the progress of this reaction in this way. The absorbance is directly proportional to the concentration. And so if we plot the absorbance here at lambda max versus time, then this is what we're going to see. The absorbance is going to decrease over time as the crystal violet reacts with the hydroxide. Eventually, what's going to happen is, if you continue to dilute this, the color is going to completely fade. And the absorbance is going to go down close to 0. Once the absorbance hits 0, then no colors are absorbed, and it's going to go colorless because all the colors of the rainbow are going to pass through. And so we're going to follow this reaction, but we don't know how it reacts. That is it going to react linearly? The color just decreases in a linear fashion? Or is it going to be non-linear? You know, maybe color rapidly decreases and then slowly decreases. So if we started an absorbance of about 1, we want at least around 90% reaction. So we want to at least go from absorbance of 1 down to an absorbance of 0.1. That would be about 90% reaction. And if we have 90% reaction, if this is non-linear, it'd take forever to go to 0. Right? If it's linear, then we could see that. And so there's going to be some playing around. And that is something like this LabQuest system here can record data every millisecond. So if it records 1 data point per millisecond, in 1 second, how many data points would we have? Well, if it's recording 1 data point every millisecond, then by 1 second, we'd have 1,000 data points. Well, it depends on how fast the reaction occurs. If the reaction occurs within a second or two, that's what we want. We want to record data at that high frequency so we don't miss anything. Because if the reaction's over in a few seconds and your first data point's 30 seconds out, then you missed everything. And so there's going to be some playing around. Well, we don't have time to play around. And so I'm going to tell you that this reaction occurs over minutes. So if the reaction occurs over minutes, do we want to collect data every millisecond? No, that's too much data. Especially since we don't have Wi-Fi. These are Wi-Fi enabled. And we don't have a USB. So what we're going to do is we're going to collect data maybe every 30 seconds. You know, if the reaction takes minutes, then maybe a data point every 30 seconds is enough. We're just going to try it and see what happens. All right, so the first thing we need to do is we're not going to record the whole spectrum, because if we record the whole spectrum, that's a huge number of data points that you'd have to transfer into your notebook. We only care about where it changes the most. Where does the absorbance change the most? At lambda max. And so what we're going to do is we're only going to collect data at lambda max. And so the first thing we're going to do is hit the top left meter. You see the scale or meter or whatever? You guys got it? Okay, then we're going to change the mode. We're going to go from full spectrum to, we're going to do time-based. So click on time-based. Now, it's duration set on seconds, but our reaction is going to take minutes. So on the durations, change from seconds to minutes. Then we're going to take 2 samples per minute. So on the first box, change it to 2. So 2 samples per minute, so a half minute per sample interval.
Wait, so duration, mine shows 200 minutes.
Yeah, 200 minutes is too long, right? So we're going to change it. We're going to change it to 10 minutes duration. So if we do 10-minute duration, collecting 2 samples per minute, we're going to collect a total of 21 data points, starting with minute 0. And then click OK.
Interval is 0.5.
Interval's 0.5.
And then rate is what?
Rate is 2 samples per minute. So we're going to collect 2 samples per minute, that is 2 data points, and hopefully that's enough. If it's not enough, then we have to tighten up the interval, because we have to think, is the reaction, does it react smoothly or does it jump around randomly? Like one instant of time, the reaction's going like crazy, the next instant it slows down, the next instant it goes crazy. Is the reaction like that, or does the reaction progress in a smooth fashion? What do you think? Well, we're just going to assume a smooth fashion for now and then see what happens. We can always adjust this. You know, these are just guesses. These are guesses, and you would do a lot of trial and error to figure this out. You have to do trial and error to figure out the right concentration to get it in the Beer's law region. You have to do trial and error to figure out what parameters you're going to use for the experiment. This is all trial and error. But the problem is when you get a procedure, you know, people just cookbook it. They don't have to think about what any of the numbers mean. They just input the numbers, right? Click OK. All right, I'm going to discard the previous data. We don't really need it. All right, now I'm going to, I want to calibrate this at the correct wavelength. What we did was a full spectrum calibration, but now that we have a specific wavelength we want, we're going to calibrate it at that specific wavelength to make sure it's properly calibrated. And so click on the red field and click Calibrate. Oops. Did I put, no, sorry. Click on the red field and change wavelength. Enter the wavelength, your lambda max. Mine was 592. Point.
First one or last one?
Probably the best is to average, but it doesn't really matter because they aren't that different. Just ballpark average. Okay, did you guys get it? All right, then click on the red field and then click change, not change, we just did that, calibrate. Click calibrate. Okay. Now, we could skip the warm-up. This has been on continuously. So skip warm-up. Put the blank inside the SpectroViz. And then finish the calibration. Calibration complete. Click OK. All right, now we're ready. With the blank in there, you should be getting an absorbance about 0, plus or minus the noise. You know, the small fluctuations. All right. Now let's talk about the experiment now.
Wait, I have a question.
Uh-huh.
When you say noise, what do you mean by that? Like, because how can you have noise? Like, what is the factor?
What causes the noise? The noise is caused by different things. One thing is the output of the light bulb. Is the output of the light bulb totally stable? No. If it were, then there'd be no noise. It'd be a straight, flat line. The other are the detection electronics. You know, how it detects the electronics itself. So typically what you're going to see, you're going to see the baseline there, like at 760 or 670, from 670 to 760. It's not totally flat. There's slight up and down. You can't see it until you magnify it because it looks totally flat. But when you zoom in, then you're going to see, wow, it goes down here, and then it goes up here, and then down here, and up here. But that's it. Today, you know, I was talking about all these absorbances, so I was checking people's data. And then I looked at this one person's data. Now, this one person's data, the first data point at time 0 was minus 0.015. And then the next 30 seconds later was 0.005. And then 1 minute later, or 60 seconds later, it was 0.010. You know, if you see data like that, does that look right? You know, what we're supposed to see is this. We're supposed to start off at some absorbance around here and then watch as the crystal violet color fades. We're going to see the color fade by this. When I see this, there's no color here. This is 0. You know, this is like pH readings. Are your pH readings, are those free of noise and fluctuations? No, not really. It's a thing when we have electronic instruments like this. And so unfortunately this data is bad. This, I think they set the wavelength, they accidentally must have set it at, rather than, 589? They must have accidentally set it at 689, and they were just measuring the flat line way over to the right. All right, so we're going to do a few trials or a few runs. So we're going to call this one run 1. In run 1, we're going to have 30.00 milliliters of reaction mixture. First, we're going to put in 10.00 milliliters of DI water. And then we'll put in 10.00 milliliters of crystal violet solution. And then finally, we're going to put in 10.00 milliliters of sodium hydroxide. So put these ones in first. And then second, do the 10 milliliters. When we do this, let's say I'm ready to add the 10 milliliters of sodium hydroxide. What happens is when you put the 10 milliliters, the first drop of sodium hydroxide hits the surface. when the first drop of sodium hydroxide hits the surface of our CV mix, it's going to start reacting. And so we're going to follow this via time, the progress of the reaction. So should we start the stopwatch when the first drop hits? Or should we start the stopwatch when the last drop of sodium hydroxide hits? Because how long does it take you to drain a 10 milliliter volumetric pipette? It would be nice if you could dump in all 10 milliliters at once, but you can't. This thing drains slowly, right? And so there's going to be a time delay. So if you start the stopwatch when the first drop hits, you're too early. You know, even though, yeah, but the bulk of the sodium hydroxide is not in there. It'll change how it reacts. If you wait until the last drop hits, you're too late. And so what we want to do is we want to average out that error. In order to average out the error, we want to start the stopwatch when we put in 5 milliliters. But there's no 5 milliliter mark on the pipette. And so you're just going to eyeball it and guess. This is about half. When about half of the sodium hydroxide has drained, do you guys have a stopwatch on your phone or something? Just hit the stopwatch. That's the 0. That's what we're going to call the start of the reaction. And so first drop, last drop is too late. First drop is too early. And so just guesstimate when half of it is entered and then hit times 0. Or start the stopwatch. Now, there's going to be a time delay because we have to mix everything, and then we have to rinse out the cuvette with this reaction mixture because we don't want to have to dry these. It's a hassle. And so we got plenty of reaction mixtures so we can rinse this as many times as we want. And then we got to fill it, and then we got to put it in the SpectroVis. By the time we put it in the SpectroVis, how many minutes of reaction have just passed? Probably like a minute. Depends on how fast you are. You know, there's some people who are taking their time and 3 minutes have passed. Well, 3 minutes have passed before they took their first measurement. The reaction was already almost over. And so you don't want too much of a time delay. You want to work quickly to get that cuvette in here, because there's going to be a second time 0. So what you want to do is keep an eye on that stopwatch, and then when you press the green start button here, then this stopwatch or internal clock goes off. And so as soon as you press that, that's going to be the 0 for your data. The 0 for your data is not the same as the 0 for your reaction, because there's going to be a time lag between recordings. All right, once we know, how much time elapsed between the start of the reaction and the start of data acquisition, then it's okay. We don't need to keep an eye on the stopwatch anymore because the clock inside here will keep track of our experiment, right? And so we just want to know what the time lag was or the time delay. And so all you have to do is put your reaction mixture in here and then hit the start. And if we did this right, a 1 to 3 dilution of CV gives us an absorbance around 1, hopefully, plus or minus, whatever. And so then this time delay means some reactions taking place. And so the initial absorbance reading here is going to be less than 1 probably, but hopefully not too far less than 1. If your initial absorbance reading comes out to like 0.015, then what do you got to think? You're too late. The reaction's already done, right? This is way more than 90% reaction. This is closer to 99% reaction. Actually, it's even more than 99% reaction. All right, any questions on this? All right, let's try the first run and then see how it goes, and then we'll make any adjustments as necessary.